Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing. This is lecture number 17, and in this lecture we will be actually talking about the various transitions which occur in the materials which are based on temperature. So temperature based variation in the properties of the materials which will be used for quantum computing will be actually dealt with in this lecture. Now we will first look into the Fermi-Dirac probability function, sort of gives you a basic idea or an idea about the energy density function and where, with respect to the conduction band and the valence band, if you are able to place your Fermi level, then it will give me the probability of finding the electron above and below the Fermi level. We will also look into the concept of intrinsic carrier concentration variation with temperature, right? And then we will look at the energy band diagram at 300 Kelvin at 0 Kelvin, and then we will see how the position of the Fermi level will vary with respect to temperature. And finally, we will end this talk with the concept of electron concentration and conductivity, and then there will be a numerical example to showcase one problem on conductivity, right? The whole idea of this chapter or this lecture is to give you a mathematical framework by which you can predict the number of charge carriers and their probability of occupancy in the conduction band as a function of temperature. That's the two things. The third thing is, after the takeaway of this lecture is that you will be able to find out how the conductivity varies with respect to temperature. Why is it important? It is important because finally when you want to find out the total current which is flowing through a device at low temperature, these phenomena will change the value of the current drastically. So as a designer or as a engineer working in this domain or as a scientist working in this domain, you should be able to handle this both qualitatively as well as quantitatively, right? So let's first come to the Fermi probability function. So even before we start the Fermi probability function, let me showcase to you one basic point and then we can move forward. Maybe I can use maybe this page to do that. Typically, all of you are aware of the fact that if you take silicon, for example, which is a semiconductor, right? And if you basically, let us suppose this is your valence band, this is the conduction band, and this is the forbidden energy gap, right, between this and this. This is the energy scale which you see, right? So it's not a, please keep in mind, this is not a spatial scale, it is an energy scale. And as I discussed with you, that conduction band is a band where above which, if the electrons are placed, they will be all acting as free electrons, and therefore they will participate in the current which is flowing through the device in the semiconductor. And if these electrons are actually in the valence band, they will be combining with the holes here, and therefore they will not be able to do that. They will not be able to. So these are bound states for electron, bound states for electron, and these are free states for electron. So let us suppose this energy is some value E, right, and you give this is kT by Q, let us suppose, right. Then if I give a certain value of energy, right, more than this band gap here, right, then what will happen is this energy band gap will make the electron shoot from valence band to conduction band, itself becoming a free and generating a hole here. So every time it flows from valence to the conduction band, it generates a free electron and it generates a free hole, right. Now if you apply therefore an electric field, let us suppose in this spatial direction, then the holes will move in this direction, whereas the electrons will be moving in the opposite direction, right. You also have to ensure that since this is the forbidden energy gap, any energy which is less than the forbidden energy gap will not allow the electrons to move forward, correct. Now if the electron is in the conduction band and if it starts to fall and come towards the valence band, then it releases this much amount of energy equal to the band gap, which is Eg, right. So either the electron combines with the holes and releases an amount equals to Eg, right, and this Eg is the band gap of semiconductor. Let us suppose one band gap is, let us say 4 electron volts, right. So 4 electron volt will be the energy in terms of this thing. This 4 electron volt energy, corresponding energy will be released when you drop an electron from hole. Now let's come to the Fermi level. So let's look at this equation. This is known as a Fermi-Boltzmann equation. Now in this equation, quite interestingly, if let us suppose E is equals to the Fermi level EF, then this becomes e to the power 0 and I get 1 over 1 plus e to the power 0 is 1, which is equals to 1 by 2, which means that my Fermi potential at EF, right, is equals to 1 by 2, which means that if your Fermi potential is kept in the middle between the conduction band and valence band, then the probability of finding the electron below the Fermi level is high and above the Fermi level is low, right. That is what I wanted to say in this case. Similarly, if let us suppose E is much larger as compared to the Fermi level, which means that this quantity will be shooting up, which means that the whole quantity will be shooting down. Therefore, probability of it finding electron goes low. Is it okay? Probability of finding it goes low. Now let us see what will happen if I take t equals to 0. At t equals to 0, if this is 0, then this becomes exponential to the power infinity, which makes that Fe will be equals to 0. So at t equals to 0, right, f of E of f goes to 0. Look at this dotted curve here. This dotted curve is the curve which is solved for delta function, which tells you that all the energies, right, if you plot this graph, like is this dotted graph, it's not shown here properly, but let me show it to you here. So this is how it looks like. Just for the dotted one, it goes like this and then it comes like this. So this is EF, right? This is you're plotting with respect to E, and this is your Fermi energy F of E of F. This is 1 and this is 0, which means that all the states below the Fermi level are all filled up. You see, the probability of finding the electron is 1 below the Fermi level. So all the states below the Fermi level are filled at t equals to 0. I will show you an example to showcase that. Let's take up a conduction band, valence band. This is EC, conduction band. This is valence band dV. And let us suppose my intrinsic, this is known as intrinsic Fermi level, EFI, is somewhere in middle between EC and EV. So EFI is approximately equals to EG by 2, let us suppose. Then at t equals to 0, all the states of the valence band will be filled up, and all the states above the Fermi level, which is the conduction band, will be empty. So this will be all empty and this will be all filled up. And that's the reason you see this dotted curve. This dotted curve is 1 below EF and 0 above EF, right? And therefore, exactly at EF, if you want to find out the probability, the average will be half. And that's the reason you see you have 1 by 2 as the Fermi potential at E equals to EF. So this is at t equals to 0, which means that energy given to the semiconductor is 0, and therefore the probability of any electron to move from the valence band to the free state in the conduction band is also 0. Therefore, all the conduction band states are empty and all the valence band states are filled up. And that's the reason you see the probability is 1 below EF and 0 above EF. Now let's do one small experiment here, and let's increase the temperature from T1 and T2. So assuming that T2 is greater than T1, which is this one. So let us suppose you increase the value of the temperature T1, right? Now what will happen is, let's concentrate on this curve. Let's concentrate on this curve, right? So all the discussion will be in red pen for this curve at least. So you see, for this curve, as the temperature has increased from t equals to 0 to t equals to T1, from the valence band it will move to the conduction band. And as a result, what will happen is, some of the states in the valence band will be empty and some of the states in the conduction band will be filled. And that's shown by this curve here. You see, if you go below EF, it was 1 till this much amount of point, but as it crosses this point of energy, the Fermi potential goes down, the Fermi level goes down. The probability distribution function becomes this. It has to cross through half at EF. That is from experimental point of view. But you see what has happened? That means, if you look very carefully, these many number of states from here to here, they have been emptied, and which has filled up is basically from this to this. This has filled up. So this is filled up and this is empty at t equals to T1. So it's perfectly symmetrical because you are not generating any extra carriers from outside. You are just trying to make electron hole. So electrically it's still neutral in that sense. And therefore, whatever empty states were there in the valence band, that many number of filled states are there in the conduction band. And therefore, this is a perfectly symmetrical graph which you see here, right? Now, let's go one step ahead and show you. If my temperature is further more than T1, let us suppose T2, right? then more number of states will be empty from the valence band and more number of states will be filled up in the conduction band. That's the reason you see now. You see, you look at this graph, look at this graph. If you look at this graph, it shows you that it has still gone down. As compared to this has gone down. Gone down primarily means that the probability has lowered, which means more the states are empty. But then it ensures that the same number of states are filled up in the conduction band. So, the takeaway from all these discussion is that the Fermi probability function is basically a function of the temperature. As the temperature goes on rising, more and more states from the valence band gets emptied and exactly the same number of states in the conduction band goes on filling up, right. And so, if you go on increasing the temperature, it will become more and more straight. But please ensure that at E equals to EF, you will always have the probability of half, right. So, this gives you a brief idea about the Fermi probability function here, right, and it relates the Fermi level with the actual value of the energy level with respect to the temperature T. Now, let us come to another important characteristics of material, and that is basically your intrinsic carrier density function, right, and with respect to temperature. If you look at the right hand side, we will follow this graph maybe later on, but let us converge on this one first, right. From any of the books of solid state devices books, you can get this expression which tells you that Ni square equals to Nc times Nv times exponential minus Ev by kT. What is Nc? Nc is basically the density of states in the conduction band, and these are density of states in the valence band, number of states which are available in the valence band per unit volume. And Ec is the conduction band and Ev is the valence band. So, Ec minus Ev will be nothing but Eg, right. So, this is your Ec and this is your Ev, then the difference between them is basically your Eg. So, this is your Eg, and therefore, I get Nc Nv to the power minus Eg by kT. Even if we do not consider Nc Nv as a function of temperature, if you go on increasing the temperature here, right, this quantity reduces, right. This quantity reduces. Please understand this is 1000 by T. So, as you move from this side to this side, basically temperature reduces, right, because temperature reduces, then 1000 by T will go on increasing. This is a log scale on the y axis, decade log scale here. So, what happened is that this is 1000 degree centigrade, then this is 300 Kelvin, then 200 Kelvin and 100 Kelvin. So, what I get is 1000 corresponding is 2, then 4, 6, 8 and so on and so forth. So, 1000 by T is equals to 2 implies that T equals to 500 Kelvin. So, at 500 Kelvin, which is this one, you get 1000 by T equals to 2. Now, you see here what is happening is, as therefore, the temperature goes on reducing, 1000 by T goes on increasing, and I am moving to the right of the graph, which basically means that the intrinsic carrier density will go on decreasing. What is intrinsic carrier density? This is basically, if you remember, it is 10 to the power 10 per centimeter cube at T equals to 300 Kelvin, right. And this is a very standard way of looking at it, because your band gap is fixed, your temperature is fixed, you very well know what is the absolute value of the number of free charge carriers available at T equals to 300 Kelvin. But this expression gives you an idea that if you change the temperature from a very high value to a low value, relatively a low value, then how does it influence the carrier? And the carrier density, quite interestingly, goes down. The intrinsic carrier density goes down as you reduce the temperature, and the reduction is more in the case of 3,5 gallium arsenide, right. For gallium arsenide, the reduction is more. For germanium, it is least, right, and that is, you see, almost exponential decrease in the value of each of the parameters here, intrinsic carrier concentration, which effectively means that the number of carriers available to you to participate in the current flow is actually very, very low, right. I will give an example. Let us take up a 300 Kelvin. 300 Kelvin, if you look at silicon, you see, that is what I was talking to. If you look at 300 Kelvin silicon, then it is basically 10 to the power 10 per centimeter cube. If you make it down to 100 Kelvin, then it is somewhere 10 to the power minus 10. So, it has gone from 10 to the power 10 to 10 to the power minus 10, right. So, even at just 100 Kelvin, assuming the same intrinsic carrier concentration does not make sense. So, one thing we have learned therefore is the intrinsic carrier concentration will go on falling as the temperature goes on reducing, and this is nothing new, like it is nothing very novel. It's a basic based on the first principles of physics for the device itself, right? So this is one thing which you should be aware of as far as intrinsic carrier concentrations are concerned. At this stage, NC/NV, we are assuming it to be obviously temperature independent. Now let's come to the energy band diagram, and let's see how the Fermi level, intrinsic Fermi level, and various energy levels are related to each other. This will explain to you. Must have done it. I can quickly go through it once and show it to you. Now, we all know that intrinsic silicon is obviously does not have any free charge carrier. So, what do you do to improve the free charge carriers? You do a doping. When you want to have an n-type dopant species, you put a donor atom. Now, let's look from that point onwards in terms of high concentration of conduction band. When you put a donor atom, which is group 5 element, is the donor energy level is somewhere very close to the conduction band. This is my intrinsic Fermi level. This is my intrinsic Fermi level. Intrinsic Fermi level. Right. So, this is my intrinsic Fermi level, and this is my donor level. And the donor level incidentally is very close to the conduction band. So, what I was explaining was the energy level of the donor atoms is very close to the conduction band edge. So, even with a very small temperature, which is not equals to very high, because you see the temperature difference, you actually require kT by Q to be equals to only this much, right? And this will correspond to a lower temperature. So, even at 300 Kelvin, most of the donor species will be able to donate one free electron to the conduction band and itself becoming a positively charged atom. So, these are all fixed atoms which are fixed here, and the electron, and therefore it becomes an n-type semiconductor. Let's look at the acceptor states. In the acceptor state, what is happening? Just the reverse. It accepts free electron from the valence band. Why? Because the acceptor states are very close to the valence band near EV, and therefore even with the low temperature, free electrons can be donated to the acceptor ion. So, acceptor ion can accept one free electron from the valence shell, itself becoming a negatively charged one, and thereby developing large number of holes in the valence band. So, this is known as acceptor state, this is known as donor state. They will generate n-type and this will generate p-type, right. I am again assuming here that complete ionization has taken place, which means that if I have put 100 donor or acceptor species, then all the 100 donor will donate 100 electron, and all the 100 acceptor species will accept 100 electron from the valence band, correct. So, one will donate to the conduction band, another will accept from the valence. When I say 100%, I means all of them. If I would have told that no, it is not complete ionization, it is just an incomplete ionization with 80% ionization, then only 80 number of electrons will be donated to the conduction band. So, I am assuming it for all practical purposes that the complete ionization has taken place, and this is the structure for a n-type and a p-type material. Please understand my Fermi level, intrinsic Fermi level is lying midway between the conduction band and the valence band. The probability there is obviously half in this case, right. Now, I have already told you here in this case. Now, you see quite interestingly what thing has happened is I have this intrinsic Fermi level remaining the same, valence band remaining the same, conduction band remaining the same. We have already discussed the donor level, which will be called the conduction band. Now, you see the Fermi level is very close to the conduction band, telling me that all the levels above the Fermi level are filled up, and all the levels below are devoid of free charge carriers. So, the Fermi level is between the donor edge and the conduction band. Smaller the distance between the Fermi level and the donor species, right, smaller the distance, more probability of finding free electron in the n-type semiconductor. Let us do a reverse thinking and come back to a p-type semiconductor, that your Fermi level is very close to the valence band. But let us suppose I would have gone and made my temperature approximately to 0 Kelvin. 0 Kelvin will imply that my energy is 0. You got the point? If T equals to 0, energy is 0. Energy is 0 implying that donor species will never be able to donate to the n-type, to the conduction band and making it n-type. Similarly, p-type semiconductor will not be able to accept any electron from the valence band, even if the energy difference between the two levels are very small, because T equals to 0 theoretically means that there is no energy involved in it. At 0 Kelvin, if you look very carefully, you will also appreciate the fact that if you go back to this slide, 0 Kelvin effectively means that your intrinsic carrier density has actually gone to 10 to the power minus 30, minus 35. So, it's sort of a freeze out has happened. the freezing out of free charge carriers available to you, right? The same thing happens at 300. This is happening at 0 Kelvin, right? So let's take up a problem and show it to you. How do I sort of work along with this problem? So the problem is that you have to determine the temperature at which 90% of the acceptor atoms are ionized, right? So I have a p-type semiconductor silicon which is doped with boron or group 3, and the acceptor concentrations are 10 to the power 16 per centimeter cube. The solution is that if you find out this is given by a formula that Pa upon P0 plus Pa equals to 1 upon 1 plus Nv by 4 Na exponential Ea minus Ev. Ea minus Ev is the acceptor ion level minus the valence level divided by Kt. If you do 90% ionization, it effectively means that Pa by Po plus Pa will be approximately 0.1, right? What is Pa and is P0? P0 is the initial condition, right? 10 to the power 16. And if I want it to be just 90%, which means that if you have a 90% donor, which means that 90% of 10 to the power 16 number of acceptor species will be taken care of. So if you solve it, you get 0.1 because 90% I get this. If you put all the values of Nv, Na are known to you, Ea, Ev, Kt is known to you, then I get that you can find out when T equals to 193 Kelvin. What I wanted to show to you is that at 193 Kelvin, only 90% of the acceptor ions are ionized, right? You can get all these discussion in Streetman book or any other semiconductor book. I'm not going to details of this one. I wanted to showcase here is that even at T equals to 193, around 200 Kelvin, only 90% of the acceptor ions are ionized, right? And that tells you the temperature dependency of the number of ionization. So let's look therefore now at electron concentration versus hole concentration. This will require some amount of understanding in terms of design in terms of this one. So what we will do is we'll take up this in the next lecture, but I'll give you the insight which we did till this much amount of time. What we did, we understood what is the concept of Fermi potential. We also understood the meaning of donor species and acceptor species and their position with respect to valence band and conduction band. What is the meaning of intrinsic Fermi level, where the probability of finding the electron is half, and also the temperature dependent Fermi level, which will be very close to the conduction band and valence band available to you. We also found out that the intrinsic charge carrier density is a strong function of temperature, and as the temperature starts to drop down, the number of charge carriers goes down. This is sort of known as a freeze out condition in cryogenics, and therefore the number of carriers available to you is relatively very small, right? So when we start the next lecture, that part of it, that the intrinsic carrier concentration dependency on the temperature, will be dealt very well in this particular diagram, right? So why is it important? Again, I just discussed with you, it is important to understand therefore the number of carriers which will be available as you move your temperature from 300 to 0 Kelvin or near 0 Kelvin, because that will be finally required for finding out the current, total current flowing through the device, and that's the reason this chapter is important. We will meet next time to discuss with you electron concentration versus temperature variation. Thank you very much.